Okay, so 5.3, part 1. Today they're basically going to give a name to and do some math symbols for the stuff we've been doing lately. What we've been doing is largely like the area underneath the curves, occasionally a volume instead of an area. If we took an area under a curve and like rotated it in the 3D world. But none of these things have really had names until today, or like math symbols. Until today, so that's sort of what today is about, is breaking that ice. So these things today are going to be called Riemann Sums. I think Riemann was like a German mathematician guy who had to do with the development of this, Newton, Leibniz, Riemann, all these guys. I wouldn't get real attached to the name Riemann Sums. That's sort of like a one-day appearance of a name, and then that's going to just sort of vanish. But I think he was responsible, I'm guessing, for the idea of the fact that these areas could be either looked at as positive if they're above the axis, or as negative if we dipped below the axis. So if I had, everything we've done has been above the axis to this point. But if I gave you something like that, we want to look at this as a positive area, this is a negative area, this is a positive area, and this is a negative area. That today we'll encounter that for the first time, I think. Things below the x-axis will be treated as negative values, above the axis as positive values. The idea here is still to partition, which is, should I spell partition wrong with too many, I got a little carried away with my eyes and my keys there in the middle. So we're going to partition, which just means split up an interval into subinterval. More of them means you're more accurate. That's still the idea behind this. We've got this thing, if we cut it in 2 pieces, that's not like great. 4 pieces would be better. 8 pieces would be better. But the more and more of them you add on, the more length it adds to your calculations, but it adds some accuracy to it. That's still the idea. Then they finally get around to introducing you to the word integral. So the integral is just a fancy calculus term for areas. Like derivatives were just slopes. Like in the Algebra 1 world, we did a lot of slopes. Calculus is derivatives mean slopes. You've done a lot of areas in your life. The calculus word for these areas is integrals. So to start to introduce you to some of the calculus symbols, we are going to bring back limits slightly, okay? But limits are going to work quietly in the background. So if you didn't enjoy chapter 2 with limits are just sort of at work. But the idea of limits is at work because we would like to get, to be most accurate, you'd like to get tons and tons and tons of these pieces. And eventually, how wide would you like each piece to be, essentially? Yeah, as close as you could get to 0. So that's why the notion of a limit is in play. You want to get really tons and tons and tons of these and get them super, super, super small, almost to a point where they're 0. Now they can't be 0, because if you had 0 width, you can't do an area anymore. But you'd like to really basically be so narrow, it might as well be 0. So what the integral is going to be is the limit. If we could narrow out the length of these subintervals, which they're going to call that length delta x, like a change in x. If we could narrow this out so it's basically 0, that's what we're after. This symbol is the Greek letter what? Sigma. Sigma means to add. We've been adding rectangle areas, which I could write as heights times widths if I wished to. The height, they're going to start to just call that f of x. F of x is the same as y. We've known that forever. The width we're calling delta x for now. And that's sort of like some unwieldy looking symbols. And so they invented some new symbols to do this. Not surprising that in the calculus world, the delta x from algebra is getting replaced with a dx. We've done that stuff before. We've done delta x as mean algebra, dx as mean calculus time. So delta x is just going to be called dx. The f of x is going to be still called f of x. So when we see problems that look like this is kind of giving us a height, this is kind of giving us a width, but that no longer really matters to us. Okay, we can just start to take that for granted. And this symbol is out. Sigma is a algebra only kind of symbol. And this really tall, skinny S is in. So just like they traded the Greek letter, this is the Greek letter delta, they traded delta for a D. So Greek is out, regular D is in calculus time. Sigma is out from Greek, and then this really skinny S looking thing is in. This S is called the integral sign. So when you hear me talking about an integral sign, I'm talking about that super tall, super skinny S looking symbol. The integrand is a word you'll hear me mention every once in a while. The integrand is just the formula that you're doing the integral of. So over there, my integrand, when I get near the end of the board, will be like an x squared or an x, like way over there by the date. Those are the integrands are just the thing that you're doing the integral of, the formula you're doing the integral of. The upper and lower limits of integration are just these letters. So if I'm talking about the upper limit of integration, I'm talking about the B. If I'm looking to talk about the lower limit of integration, we're talking about the A. The directions that you're going to see as you go to do problems on homework and quizzes and tests and things, if it says evaluate the integral, it means to do the stuff that we'll be doing when we get over to that last column of problems. Or to make that a verb, to integrate something means to come up with the number for it. So here's what this means in a graph world. And there's not graphing really a lot in this, but there will be continue to be a little bit of graphing in this chapter. If you have a curve, call it y, or call it f of x, call it whatever you want to call it. If I wanted to find the area between A and B, from A, we draw a line straight up until we hit the curve. From B, we draw a line straight up until we hit the curve. That would create a zone that we could compute its area. That's what that thing measures. This is the integral from A to B. So it started at A and it went to B. F of x would be the name of the equation that caused the graph. And the dx is almost just sort of like a decorative thing. It's like the parsley on your plate when you go to a fancy restaurant. It doesn't do anything other than just sit there. It's just a garnish, it's just a decoration. This dx is no longer really functional to us. All the problems you've done up to now, you've done heights times widths, and you chose the widths. They're choosing for you. This width is so narrow it doesn't really even matter anymore. But it's always written in every problem, but it doesn't impact your life in any way other than to just like sit there. 25% of the time, I'll forget to even write the dx because it doesn't do anything in the problems. But anytime you see this symbol, this integral symbol, you're going to see one of these dx guys just kind of coming along for the ride. And I actually remembered them all on my board, so good for me. So basically all we did is this symbol has meaning now. That's what we accomplished in the last 5 minutes. It's just a reference to what the area is. Instead of using words, we've got a symbol that means find that area now. These rules are not worthy of being on your card, in my opinion. They are probably worthy of going in your notes to use for one night's worth of homework, but these aren't like permanent card-worthy things. This first one I think you might be able to reason out. If I asked you to do the integral, find the area from A to A of some sort of a formula, how much area do you think that would be if we didn't go from A to B, but we went from A to itself? How much area would that make? 0 is correct. Second rule that we'll use a little bit in this homework, instead of doing the area from A to B, if I asked you to do the area from B to A, but I kept the formula the same, there would be 2 reasonable guesses for this. One of them's right, one of them's not. How do you think the area, the integral from A to B, would compare to the integral from B to A? You could argue that they're the same. They aren't going to be the same, but they're close. It's the other option that's reasonable that stands the test of time. Like if the area from A to B is 8, what do you think the area from B back to A would be? -8. They're going to be numerically equal, but opposite signs. This rule is just letting you know derivatives in one way work the same way integrals are working in our present. If you wanted to do derivatives in the past, and there was a formula sitting there, but also a number, you were able to just always do the derivative and worry about the number later. For example, if you wanted to do the derivative of 10 sine x, you could just do the derivative of sine x, and the 10 just falls along. Integrals do that too. If they ask you to do the integral of some number multiplying the formula, you can just do the integral of the base formula, and then when you're done, go ahead and multiply the number on there. That's not earth-shaking, but derivatives work like integrals in that sense. Another way that derivatives and integrals work in the same way is if there's adding going on. If I want you to do the integral of an adding zone, you can do the integral of the one piece of it, separately do the integral of the other piece of it, and just add the pieces together. Like if I asked you to do the derivative of 10 sine x plus x squared, you wouldn't go, oh my goodness, how will I do that now? It's so much bigger. You would just do this one, you would do that one, you just continue to add them up, okay? So that's what this is telling you. If you go to do integrals, same concept as when you used to do derivatives. If there's some adding going on, just do each piece individually and just worry about adding them later. And here's one I think you could figure out on your own. If I want you to do the integral from a to b of some equation, then the integral from b to c of that same thing, what do you think that would make? The integral, or I could just substitute the word area anytime I want. The area from A to B plus the area from B to C. The area from B to C. It would make the area from A to C of that same equation. Question about the rule. More rules that are worth being in your notes, but not worth being on the card, because these also won't really stand the test of time. If we want to do an integral from A to B, and it's just a number in the problem, we can take just that number and multiply the upper limit minus the lower limit. If I work an x into the problem, we can go upper limit squared dividing 2 minus lower limit squared dividing 2. If I want to do x squared, we can go upper limit cubed dividing 3 minus lower limit cubed dividing 3. And those are going to guide you through some homework problems. When you go to do the homework, these last two sets of rules are going to largely guide your life for at night. Again, they're not going to be around forever. Because I think you would realize the most effective way to do this would not to be take every possible thing that could be in a problem and have a rule for it on a card. That's rough. You don't want another rule for x cubed, x fourth, x fifth, x sixth, x seventh. Another rule for sine, another rule for cosine, another rule for roots, another rule for, like, it's too much. For today, this will get us through that, okay? But long-term, best solution is not have a rule for every scenario that you have to look up. There's going to be a way to do this. And the book gets real excited and think it's like it was a huge deal in the history of math when they sort of figured out a trend on this stuff. Question about the concepts. So here's like 3 problems. You don't need any of this anymore, do you? One bunch of homework is going to operate off this first set of rules. Another bunch of homework that's a little bit more useful is going to operate off the last bunch of rules. Will be another day here. I think the tomorrow thing involves a little bit of graphing, if I'm remembering the sequencing right. For the one group of homework, they're going to give you, they did an integral of a formula called f using those numbers, and they got 5. Then they did some different numbers, still operating on stuff called f, and they got a different result. Then I'm back to the original numbers with a different formula. I call it H. And they got an entirely different result. So they'll give you a couple things like that to act as like a foundation to work on, of things that you know. And then I can switch some stuff up and say 4 to 1 F. A thought on what 4 to 1 F would be, it would be 2. This looks the most like this. I changed the limits of integration, I changed their order, and that changes their sign. That's this rule in action. If I go from -1 to 1, you're looking either at first or last. It depends on what I asked you to, because those are the ones with the limits that are correct. I'm going to go 2 of the F's plus 3 of the H's. And really the dx, I should probably do something like this. Even though the dx doesn't matter, the dx goes with everything. I think I had a rule over there where I didn't really do that. This one, I really should have made the dx go with the whole problem, but it just seemed like unnecessary punctuation. A thought on this? It is 31. 2 of the F's, just grab the 5 from above. 3 of the H's, just grab the 7 from above. 2 5s and 3 7s. That's 31. If I go -1 to 1, again, I could be looking at either of those. If I go F minus H, and then I just have to do the brackets again to keep the dx going with everybody. F's minus H's. -2. Then I'm going from -1 to 4, which I don't have anything up there going from -1 to 4, so this is a different scheme. But I'm going to go f of x dx. So if I'm doing f of x dx, this clearly has nothing to do with it, because that's only h-based information. It has to have something to do with that stuff. A thought on how I could go from -1 to 4?
That's 5 and -2.
Add the 5 and -2. It is, it's this last rule. That if we go from -1 to 1 and take a break, but then continue from 1 to 4, if we'd add those together, because this ended with a 1 and this resumes with a 1, if we add them together, it would take you on the full journey from -1 to 4, and that would end up being 3. Question about usage of those rules? Click this out of there. For the last group, I'm going to go integral from 2 to 3 x squared dx. And then I'll go bigger from 0 to 2. T squared over 4 minus 7t plus 5, and then the decorative dt that just has to go with everything. So we're working these rules, if I could call them A, B, and C, just to make our communication even a little easier. So this, you look at rule C, because it's the one with the squares in it. And then we just have to plug in our numbers. So this cubed is 27. I'm going to put that over 3, even though that feels awkward to put it over 3. You probably are like, divide it, make 9. I'm going to say no thanks. Because I need to subtract another thing that's going to be over 3. So to help my subtracting in the long term, I kind of like to just keep my common denominator around for this. What's this going to do? Subtracting gets me, and there we go. Question about that? this one, the t squared is going to head you to formula C again. But there's going to be a 1/4 that we're just going to kind of slide out of the way using this idea. If there's a number multiplying something that we see as familiar, you can just slide that out of the way. Worry about the multiply part of that later. So let's do the t squared formula again, which is stuff over 3's.
What's at the bottom of the head? Is it a 0?
0, yeah, we're from 0 to 2. So this would be 8 for the first one, always use the top first. 0 for the second one, so that's how that goes. -7, we're just going to isolate the -7 out of the way. And with the t, we use formula B, which is stuff squareds over 2's. So stuff squareds over 2's, you get -0. And then for the 5, we'd use formula A, which is to take the 5 times -0. And this one's maybe artificially a little bit easier because I used 0. And if you're doing this problem in your life, you might have chosen to not even write this down. I just did that all the way out, because generally speaking, you do have that subtracting back half going on anyway. Well, this piece is nice and easy now, makes 10. This piece, 4 divides 2 evenly, 7 factors into that, you got 14. This piece, fraction stuff goes so great, saves a fraction, gets you 2/3. Try to put all that together to get a final result. Yeah, I agree with that. Also acceptable -3 and 1/3 if you prefer to do that. Since you've got a -4 out of these, -4 definitely overcomes the positive 2/3. It's got to be a negative answer. Again, we're not graphing, I don't think, anything today, but this is something that if we did graph it, it probably has like a little bit over and like a lot under. That there was probably some positive area to something, but there's probably a lot more under the axis negativity than there was positivity. Or maybe it was just flat out all under the axis. It's hard to know for sure, but negative means it got under in some way. More unders than overs. That's the idea of the day. Again, these aren't hard to navigate, but long term, it's not best practices. That's not the best way to do these integrals, to have all these crazy formulas you have to look up all the time. So I put them in your notes, use them tonight, but don't get married to them, because there's going to be a better overall approach to this coming. I think they're just kind of guiding you a little bit. This chapter kind of guides you a little bit through history, the way it worked for the people at the time. Like this is how they evolved the math, and they're just taking you on that journey, I think, with them through history. 300, we're today up to 18. The first 6 are like these. There's some ABCD-ness to them, I think, but the first 6 are like these problems where based on the rules that I have already erased. Then from 7 to 18, 7 to 18 is like what we finished with. That's based on the second set of rules that I just labeled ABC, and that'll take you on a journey. 19, we'll learn how to do stuff from 19 to like 30-ish, I think, tomorrow. Those will have to do with a little bit of graphing activity on those. A lot of the same ideas still. That's it for me.